Okay, with that clarified, I'm pleased to give an introduction about our speaker today. So Pascal is a postdoc researcher at the University of Cambridge working on low-speed unsteady aerodynamics from the experimental perspective. So he completed his PhD at Cambridge under the supervision of Professor Babinski in September 2021, throughout which he experimentally investigated the unsteady flow and the force response around flight plates and cylinders, with the aim to elucidate the underlying principles governing their development to aid the development to predict low-order models. So we are pleased to welcome Dr. Gehlert and learn from him. So Pascal, thanks for joining us today.
Hi, thank you for having me. Maybe just very quickly before I get started, can you see my cursor on screen? So if I point at things, can you see that?
I do, I can see that.
Yes, yeah. Okay, wonderful. Yeah, thank you very much for having me. So I'm still at Cambridge doing my postdoc now. But the work I'll be talking about is all comes from basically my PhD and some of the work that's been going on there in regards to low speed unsteady aerodynamics, where low speed is roughly the Reynolds numbers of 20,000 plus or minus. So, you know, what you have for small drones, birds, something of that order. And what we've been doing is we've been looking at it from a vorticity perspective to better understand the flow. And that sounds maybe a bit abstract, but hopefully throughout this talk, you'll understand a bit more with what I mean by that. So just to have a very brief overview of what I'll be talking about. So I'll try and start off by briefly just talking about unsteady flow in the world around us and how low order models can really help us in those situations. I'll then move on to looking more in detail into the unsteady boundary layer, decomposing it into individual contributions, and then relating these to the added mass force and how this can sometimes cause confusion. And then we'll look at the unsteady separation. So obviously separation is normally very, very important for the whole force development. And we're going to look at looking at the behavior of the boundary layer at this unsteady separation point and seeing if we can make more sense of what's going on there to help us then in the future predict or just better understand the unsteady separation process, I suppose. So yeah, unsteady flows, they're really everywhere around us, from, you might say, maybe from the more mundane or less critical scenarios of we have a rear flap or rear wing of a Formula One car. They can open and close their rear flap, and if you close the rear flap, then in that motion you would generate a vortex, so a very unsteady flow field. But you also have them, for example, if you're in urban canyons, in cities, or even in forests, and you have flow coming in from any direction, and then it sheds from buildings, from the sides of the buildings, and creates vortices, and through that creates a very turbulent environment. Where, for example, if we have small drones that we, I don't know, for example, if we use to deliver parcels in the future, or even during after disaster relief. So for example, you had a big storm and it's still very windy outside, and you really want to be able to fly your drones to look for survivors. But if it's too windy, then you're limited to what gusts they can withstand. So that's where we are very heavily affected by these turbulent scenarios. Of course, if you look at the animal kingdom, and hopefully this transmits well over Zoom, but you have a hummingbird being attacked by its friend. But most importantly, if you look at the motion of the wings of any insect or any bird, it's very unsteady. It changes very quickly in time. And the importance of that is that we often want to borrow from nature, I suppose. So we want to borrow that flying motion and transfer it, for example, to drones. So then we really need to understand how this unsteady motion, how it impacts the flow field and how it impacts the forces, so that we don't have our drone crashing. And then finally, even real or larger scale aircraft, when they come into land, can experience turbulence, can experience gusts, and you don't want them to lose control during the most critical part maybe of their flight. So in all of these situations, what you would, I suppose, ideally have is a way to very, very quickly predict the forces. And one way of doing this is using low order models. So here rather than solving the full-on Stokes equations, which I suppose we can simulate them, but that takes, depending on what you do, ages. So it's not feasible, not practical. We want to really reduce the most important physics, or narrow down what the most important physics are, and only model these using very, very simple equations, ideally, so that we could have, we could within a split second compute what the forces are. And if we could do that, then we could, someone's drawing. Then we could, for example, have a very fast design and optimization strategies, for example, for airfoil shapes or whatever it is that you're looking at. Or alternatively, you could come up with control systems that can be used for gust mitigation. So you could imagine you have your aircraft flying around, your little drone. You measure the flow just above, like maybe 30 centimeters or just next to you through some sort of sensor. And the moment you recognize that there's a change in velocity, you can, then you've got a split second between when you measure that change in velocity before it actually, gets to your aircraft and affects you. So if in that split second you can compute what the forces will be, then you can very proactively track force and then make it to withstand forces much, or turbulent environments much, much more. So that's kind of the main gist of why we want to understand the flow field in order to basically develop, I suppose, these low order models as one big beneficiary of that. And we often do this, or the reason, I suppose, why unsteady flows are also so possibly dangerous is that the force changes very, very quickly. And we can, so what I've tried to draw here on this y-axis is the force, and then x-axis is just time, or in this case, distance, I suppose. And if you think back here, we have a steady force. Then initially, during the unsteady process of it, during the transient phase, you can exceed the steady state equivalent in terms of forces, which then obviously makes these, for example, gusty situations much, much more dangerous. And one way how we compute forces, I suppose there are many different ways of approaching the way, but one method is to decompose the total force that you have into smaller sub-forces, if you will, and then solve each one of those individually using a more simple process. And then at the end, you recombine the two. And if you do that, though, you really need to make sure that you know what exactly you're defining as each sub-component of your forces, so that you don't accidentally have an overlap between the two. So one way that we, I suppose, look at it, and again, there's many different ways, many different names of calling these things, but is one is by composing it into an added mass force and then into a circulatory force. So what is added mass? Well, added mass, you could think of, you've probably all experienced it before, if you're in your swimming pool and a friend throws in a ball right next to you, or just maybe a couple meters away, and you get there as quickly as possible. Then if you try to, and you're stationary, you try to accelerate really quickly and try to kind of sprint over, then you might have noticed that that's really, really difficult than if you moved over and accelerated more slowly. Likewise, if you were swimming and you're doing breaststroke, then maybe you would notice that as you move your hand through the water, you feel much more resistance if you accelerate your hand rather than just moving your hand at a constant velocity. And that's the added mass force in action. What physically is happening, one way of thinking about it is, if you think of yourself as being this little cylinder here, and it's in water, and it's moving from right to left, then as it moves from right to left, it needs to occupy the space to the left of it, which is currently occupied by water molecules. So of course, as the cylinder moves into this space, it needs to move these water molecules out of the way. It needs to accelerate these water molecules out of the way. And that gives an additional, that feels like there's an extra amount of mass that needs to be accelerated. So that's this one force. It's an added mass force, and that persists while we're accelerating. So that's one force component. And we can very easily calculate it from potential flow, from inviscid potential flow is one way of calculating it. And then the second force component, just to complete the picture, is you could call it maybe a circulatory force because it's related to circulation that you've shed in form of vortices. And depending on how they move around, they then create a second force component. So yeah, having said all of this, everything I'll be talking about will be two-dimensional flow. So obviously I know three-dimensional flow exists, but that does complicate things a lot, and we got to start somewhere simple, I suppose. So yeah, everything's going to be two-dimensional flow, and we're going to be trying to relate the real world or represent the real world in terms of potential flow throughout this entire talk. So what does an unsteady flow look like, and why do we want to look at it through the lens of vorticity? So here we've got an example of an unsteady flow. What you'll see in a moment is there's a cylinder here in the middle that's going to start from a stationary start and move from right to left. It's also going to spin clockwise, and we're seeding the flow just with a mixture of soy milk and alcohol to get the density to match water. So we're doing all our experiments in water. And what you now see is, if we set this off, is we see a vortex, maybe you can call it a starting vortex, developing at the bottom, and that then slowly advects away from the cylinder, whilst at the same time you get a vortex forming at the top. And really this video is here for two reasons, but the first one is just to show you how unsteady the flow field is. So consider that our cylinder is moving very slowly at the moment. So actually this is all, if you sped up the motion of the cylinder, you could really imagine how quickly the flow field is changing. And the second one is to demonstrate that really all of this could be looked at in terms of, I suppose, vorticity in some shape or form. So you initially have the vorticity related in the boundary layer. So you have your no slip condition at the wall, you have some free vorticity, some free flow velocity, and then you end up with some vorticity in the boundary layer. And then at some point when the flow separates, at your unsteady separation point, this vorticity moves off into the flow field and forms your starting vortex. Now, if we started off with a flow field where we had zero circulation, we know that we need to conserve circulation. So that basically means that all of this red or counterclockwise vorticity that we had in our starting vortex needs to equal an opposite amount, needs to reside within our boundary layer, which potential flow. We really wanted to simplify all this. We could just imagine it as 2-point vortices that create some potential flow streams that look something like this. And the reason I bring it up is that actually vorticity can be really, really useful if our aim is to better understand what's happening with the flow, but also importantly, what's happening to the forces. So Lam showed us that you can relate the position or the distance that your two vortices are apart and the strength of your vortices to the momentum in the flow field. And then because we know that the rate of change of momentum gives us a force, we can take the time derivative of this, and then we get a force. I'm saying basically that if these two vortices move apart or come together, or if their strength changes, we get a force. Now, real flow fields aren't usually made up of two vortices, but you've got lots going on. You've got your starting vortex, you've got another vortex, you've maybe got some vorticity that was generated by some alternative mechanism, and you've got your boundary layer vorticity. But because we know that we need to conserve circulation, so that means that we need to have equal amounts of red positive or blue negative vorticity. You could imagine that you basically have these vortex pairs that we saw in the case of Lam in any real flow field, or in most at least, as long as you're capturing enough of it. So that means we can just use this exactly the same approach. And this is what Wu did, and we or amongst others, and we call it the impulse method, which then means we can just look at how each of these vortices in our flow field changes in position, changes in strength, and from this arrive at forces. Where the other really, really great thing of is by viewing the flow field in terms of vorticity and in terms of potential flow, is that we can consider the total flow field as a superposition of each of our individual elements. So, we've got one starting vortex that induces some flow velocity everywhere elsewhere. We've got some free vorticity, but each of these vortices induce flow velocity, and then the superposition of all of that recreates the total or the final flow field. And we'll make use of this superposition principle in a moment. Now, all of this brings us to the two main questions that I would like to answer today throughout this talk. And the first one is looking at what is the link between the contributions to the unsteady boundary layer and the added mass force, just because sometimes there can be a bit of a confusion that can arise from this. And then secondly, what influences the boundary layer vorticity strength at the unsteady separation point. And this later point is really there because we want to predict the unsteady separation point. There's many ways of doing it. The leading edge suction parameter is one really big one out there at the moment. And they all somewhat in some shape or form, I suppose, relate to the boundary layer vorticity. So it's really trying to understand a bit more, okay, why is it behaving the way it is, so that if we understand that better, we can then more easily find up until what point do our models work, why do they work, and maybe why in some regimes do our models no longer work. So let's begin by tackling the first one and looking at boundary layer vortex sheets, and then eventually how they relate to added mass. So have some boundary layer vorticity. So in the world of potential flow, we basically condense our vorticity down to an infinitely thin sheet. And that's what we call a vortex sheet, which we define by difference in velocity, basically on either side of our vortex sheet. And using this and using the superposition principle, we can now look at the total boundary layer vortex sheet of a cylinder, which I called gamma B throughout the talk. And we can look at individual contributions that it is made up of. So the first one is if our body, in this case, cylinder, but it can really be any body, if it's spinning, then what that means is that the wall will have some velocity. We then imagine it's spinning in still air or in a still fluid, which means we have zero flow velocity outside. And then our vortex sheet, which we'll call gamma R, or the rotational vortex sheet, is simply the difference in velocity due to the velocity at the wall and due to the velocity at the flow. And in the case of our cylinder, because it's symmetric, that vortex sheet strength here on the y-axis of our graph is the same everywhere. Now, if our object is also moving or translating, then we can use the exact same approach. So we could define the vortex sheet that is related to this. So the flow has some velocity, the wall has some velocity, in this case, zero. And then this gives us a vortex sheet, which in this case is a sinusoidal distribution. So you have negative vorticity at the top of our cylinder and positive vorticity at the bottom, where if you do the math from potential flow, you can see it scales with sine and with the velocity it's traveling at. And this is quite an important or interesting feature of it, actually, that it scales with velocity. Because if you remember, or I don't know if I actually mentioned it, but your added mass force scales directly with velocity as well. And we can now make use of the idea that we mentioned a couple of slides ago when we looked at how the rate of change of the strength of vorticity can be directly linked to a force. So if our cylinder, for example, is accelerating, then the velocity u changes, which means the vortex speed, for example, in this situation would grow. And then applying the impulse method to the vorticity within our vortex sheet gives us a force, which is just down here. And again, it scales with the velocity we're traveling at. And this force actually that you calculate from this is exactly your added mass force that you could have otherwise derived from potential flow. And because of this link between because the rate of change of this vortex sheet is related to an added mass force, we in this case just choose to call it an added mass vortex sheet, but you can call it an inertial vortex sheet or whatever. The exact name isn't really that important. It's just important that you know where it comes from, I suppose. Now, there's one more vortex sheet contribution that we need to consider, and that is if we have some free vorticity in the flow field. So we have our vortex here, and this vortex induces a velocity onto our body. And to enforce, I suppose, that the induced velocity doesn't go through our boundary, so to enforce the no penetration condition, we need a corresponding vortex sheet that causes no through flow. So that's why we have a third vortex sheet component, which I'll be either calling gamma C or gamma circ or gamma circulation throughout this talk. And then if we add all of these wonderful contributions, then we end up with our total boundary layer vortex sheet. So this is all the theory, and a lot of it was done by Eldridge, by Graham, and by Corkery. They all have great papers on explaining this and also proving some of these things. But I just wanted to show you an example of that this does all actually work for not just flat plates. We'll get to those in a second, but also for bodies of volume before we proceed. So to do all of our experiments, we're going to be using a cylinder for quite a large chunk of them. And I suppose that's because usually maybe we would be using wings because that's what we're often interested in. But by simply having a cylinder and rotating it, we can change how quickly we rotate. And then that gives us a different lift force. And importantly, it also gives us a different flow field, which means that we can test lots of different scenarios without needing to constantly change the actual geometry. And in our case, we're using a water tank for it. It's 9 meters long, it's 1 meter wide, and roughly 1 meter high that we fill it up with water. And then onto this, we vertically mount whatever we're testing. So in our case, it will be a cylinder, a plate, and a scoop. You'll see that in a moment. It's connected to force balance, and the carriage here just moves the length of the tank. And then to acquire our data, we shine in a laser sheet from one side, we shine in a laser sheet from the exact opposite side. And that's so that we can get rid of any shadow regions. And at the same time, we have a camera upstream of our cylinder or of our body that we're testing and downstream. And that's so that we have optical access to everywhere in the flow, which means we can really recover the entire flow field around our object. And yeah, what does something then look like? What does the result of all of this look like? It's just a frozen frame of a cylinder, and you're looking at the vorticity contours. So blue is clockwise or negative vorticity, and red is counterclockwise or positive vorticity. So from this, we've got a boundary layer, and we now want to calculate what that boundary layer vortex sheet strength is in our case, so that we can compare it with our theoretical predictions. So what we do for this is we look at what we do is we take our cylinder, we split it up into lots of little wedges. For each of these wedges, we then define a little quadrant, and then we integrate the velocity aligned with this quadrant to get our circulation. And then what we can do is we can simply divide the circulation through by the arc length of our segment, and then this gives us our vortex sheet, or our boundary layer vortex sheet strength. And putting this into action, at the top, you'll see a video of vorticity of a cylinder that is purely surging. So it starts from stationary start and then accelerates. And at the bottom here in black, what you'll see is the boundary layer vortex sheet that we measure through the method I just described. So in terms of axes, obviously y-axis down here is the strength of our vortex sheet. X-axis here is the position on our cylinder, where the left side of it is basically the top of our cylinder, and the right side of it is the bottom of the cylinder. And let's let this walk through again. But basically, so we start off with our boundary layer vortex sheet in black, and what I've now superimposed onto this is the theoretical added mass vortex sheet in red. And we can see at this point, they both match perfectly, basically. And looking at the streamlines that we have in this situation, so here I've taken a snapshot and plotted streamlines on it, we can see these are very reminiscent of what we see in potential flow. So I suppose it's no surprise that our added mass vortex sheet, which developed as we started to accelerate, matches the theoretical prediction really well, but it's a great sign that we can actually physically measure this. And it's not just a theoretical concept that we use, but we can't extract that in real life. Now, as we continue to move, we'll see this vortex sheet grow as we continue to accelerate. And now at some point, roughly here, you can see that our real boundary layer vortex sheet departs from the theoretical added mass contribution though. But I guess that makes sense, because if we think back to what we said earlier, we have one added mass contribution that is always there, But if we have some free vorticity, which I've masked basically the cylinder and all its boundary layer vorticity, and just showing the free vorticity, then we see, well, this also needs to generate a vortex sheet contribution. And we can just calculate this by basically finding the free vorticity, putting mirror images of this vorticity into the inside of the cylinder, and then finding the slip velocity along the cylinder surface. And that's what gives us this squiggly line down here, which is our circulatory vortex sheet. And now one more thing we can do is we can say, well, we set our boundary layer vortex sheet equal to added mass plus the circulatory vortex sheet. So we can simply rearrange that for the added mass vortex sheet. So to demonstrate that this added mass vortex sheet really persists throughout the entire motion of our cylinder. So we measure the boundary layer vortex sheet, and from this subtract our circulatory contribution, which are these blue lines, blue X's that you can see dancing around. And we can really see that throughout this whole motion, these blue X's basically lie right on top of our theoretical prediction. Only at the top here and at the bottom, there's a small deviation, which corresponds to where we're actually shedding vorticity, where it gets a bit iffy, this method. Now, that works really well for a cylinder. It actually also, obviously, and this was the work by Simon and by Graham, works really great for flat plates as well. So just to prove that point, we have some vorticity contours on the left of a plate surging from right to left. Again, you see your clockwise and your counterclockwise vortex. And then over here, if we look at our individual vortex sheet contributions, we see that we basically have zero bound circulation. We have a circulatory component due to the vorticity we shed. And then we have the red crosses here are our experimental added mass vortex sheet. And the black line was the theoretical contribution. So that means that in these situations, we could have tracked how the added mass vortex sheet changes. And from this measured exactly what added mass force is. And that would have been one really good way of getting that force component in our lower order model. Now, so to recap, basically, an added mass vortex sheet is created when our body accelerates. And importantly, it's related, ignore all of this math, but just see that it's related to our body accelerating. And this remains in place even once we finished acceleration, but just stays constant. Then if flow separates, we have an additional vortex sheet due to the shed vorticity. And if we add both of these together, we end up with our total boundary layer vortex sheet. Now, let's take a look at this added mass vortex sheet a bit more, because I said we could link it to the force that is created when it changes. So what happens if it's not our body accelerating, but it is instead the fluid accelerating? Where we know we have equivalent force that we end up plus a buoyancy force. But really the question is the origin of this force the same? And the importance of that is that if we decompose forces into individual subgroups that we add together, we need to make sure that we really do know the real origin of each of these forces, because otherwise we might be double counting them. So now let's look at an accelerating flow field where the body is stationary. For reference, here in the middle, we just have the old flow field that you just saw moments ago of our body accelerating. And now here on the right, we're going to have the flow accelerating from left to right past our plate. And in the bottom right quadrant down here, what we're plotting, I'll just play this again just so that you can see it all move, is we've extracted our individual vortex sheet components, and we measured the boundary layer vortex sheet, measured the circulatory vortex sheet due to the shed vorticity that we see here. We subtract both from each other to arrive at what we previously called the added mass vortex sheet. We get these red crosses. We see the shape is exactly the same. So there appears to be no difference whether we're accelerating or whether the fluid is accelerating. And at this point, you might very rightfully say, well, obviously, Pascal, that's going to be the case because the effective velocity or the slip velocity difference between our plate and our free flow is exactly the same in both cases. So obviously the vortex sheet is the same. And that is true, the vortex sheet itself is the same. But the question is, should there be an added mass force when the body remains stationary, or is this force caused through other means? Because consider how the flow accelerates. You have some blob of fluid, some region of fluid, and then that accelerates. And you never have the entire fluid domain accelerating, but there will always be some boundary to it, which in most of our cases, and if you're an experimentalist, I suppose, would be the wind tunnel or water tank walls. And along these walls, you would have vorticity forming, you would have a boundary layer forming. So this external vorticity, likewise though, needs to create a mirror image on our actual boundary layer. And this is what we want to show now in this next step, is that actually, how did we create our accelerating flow that I showed a moment ago? Well, what we did is we used a scoop, so something of this U-shaped shape here. We kept our plate stationary, and we accelerated this scoop to push water past our flat plate. And by doing so, we create positive vorticity at the top and negative external vorticity at the bottom. And just for completeness, so that you have a sense of what actually was happening, just a little schematic of all of this, where we basically had our plate, which was stationary. It was held by an arm that connected to it. And then we attached these side skirts to a plate to form these walls. And then this just moved in. So this is the flow field I showed you. But I suppose I was tricking you a bit, because the real flow field is actually much bigger if we zoom out, and this is what the real flow field looks like. So you had this little section in here which I showed you before, but really you also have all of this free vorticity at the top and bottom that is created, and you need to deal with that appropriately, so to not confuse things. Because what you see is that if you look at your flow field and you mask out, you don't consider any of the vorticity that is shed by the plate itself, but you only consider the scoop or the external vorticity, and look at what vortex sheet it creates, which is, I'll call it gamma scoop circ over here, and those are the red crosses that I'm plotting. Then you can see as our scoop accelerates, the vortex sheet formed by this vorticity has exactly the same shape as what we previously called an added mass vortex sheet. So what that means is that if we say, well, okay, our boundary layer vortex sheet is made up of, it can be made up of an added mass contribution, can be made up of some vorticity shed by the body itself, and can be made up of some external vorticity, that in this current situation, we really don't have an added mass vortex sheet. But the distinctive shape actually comes from this vorticity created at the scoop edges. So to answer our first question, what is the link between the unsteady contributions to the boundary layer and the added mass force? And maybe more in particular, where does the force originate when it is the fluid accelerating rather than the body? And that really comes from non-body shed or external vorticity. So in our case, the vorticity created by the scoop. So the added mass force, I suppose, or the inertial force, if you want to call it like that, for a surging body is exactly the same as if the water accelerates, as if the fluid accelerates, but the origin is entirely different. And that's really, really important to consider, because otherwise you might double count things. So imagine a situation where you have your body, you're testing in a wind or water tunnel, and you're doing particle image velocimetry, and you capture some of the boundary layer vorticity in the wall. And then depending on what calculations you do, you end up with, and so if you consider what you see in the flow field, and then on top, because you add on a theoretical added mass vortex sheet, because you think that you need to add that on top because the flow is accelerating, then you just consider the same thing twice. Similarly, you can have this in a gust encounter. So I've tried to show here vertical flow moving upwards. You have two gust shear layers that find the edges of our gust. And again, if we use all the vorticity in our flow field to calculate vortex sheet contributions and then the related forces, and then on top of that, add a theoretical added mass vortex sheet and force, because we don't think it's already been considered, then we really consider the same force twice. That's why it's just important, whatever names you give these sheets and forces, that you make sure you know where they actually originate from. Now that we've maybe understood, if I've explained it reasonably to some extent, well, we know the individual contributions to the boundary layer vortex sheet are, where they come from. And now we're going to make use of those to better understand how the boundary layer vortex sheet behaves at the unsteady separation point. So this is looking at our second question. How does the boundary layer develop at the unsteady separation point? And for that, we'll return back to our cylinder and we'll have it accelerate once more. This is the same case you saw previously. So we see it accelerate, we see some blue, some red vorticity that was initially attached, but maybe now you can see that it's beginning to detach, or at least we can now see it. And what we have down here at the bottom left is the vortex sheet contribution, or just our total boundary layer vortex sheet. And we can see these discontinuity here, top and bottom as before. We can see this continuity here in the vortex sheet, and at the top, which I've marked in the vorticity field as a circle and a triangle. And these really just mark the points of unsteady flow separation. And what we're also going to add onto this diagram at the bottom is a line representing the current strength, or the current strength of the vortex sheet. And that's because we now, as this cylinder moves, we want to track how does the vortex sheet strength at the separation point develop as the flow field develops. Because ideally, you would maybe say, look, there's a critical threshold that if boundary layer vorticity for a specific object exceeds this specific value, then we know we have flow separation. So that would be a very, very useful bit of a tool and for our low order models. So let's see if that works or how it behaves. If we just let this play, and we can see the flow field evolving, we can see the vortex sheet down here evolving. What we might unfortunately notice is actually the discontinuity that we saw in our vortex sheet, which is simply where the vorticity leaves the boundary layer, is now at a much higher, much more positive, much more negative value than it was before, showing us that the raw vortex sheet strength unfortunately cannot be used to predict separation. But with the knowledge though of the individual contributions to this boundary layer vortex sheet, can we do a bit better? Can we try and understand why this vortex sheet changes and why the strength at the separation point changes? So we said we know that the boundary layer vortex sheet is made up of contribution due to rotation, due to translation, due to motion, as well as due to vorticity. So in our specific case, I mean, it wasn't rotating, so we clearly not be influencing anything, but we are accelerating. So maybe let's look at this contribution first and see if that's important. So to show this is we know that our boundary layer vortex sheet due to translation scales with velocity. So we can create a new boundary layer vortex sheet parameter, but we simply take out the influence of instantaneous velocity. So we divide through by velocity. And now we just look at this plot again, the same plot you saw before. So let's mark on the strength at the separation point. And now let's let the flow field develop. And as you can probably see now, the black line dances around, the unsteady separation point shifts, it shifts upstream, but the strength at which we're shedding seems to remain very, very similar. Now, a lot was going on in this picture. So let's look at a couple of still frames where the circle marks on the separation point, and we're only looking at the bottom portion of the cylinder now, with the boundary layer there. And as we just step through in time, what we see is that as the flow field evolves, the strength at which of the boundary layer at which we have separation is basically the same, or almost the same throughout the entire motion, which is now much more useful if we wanted to predict separation, for example. That is even though the flow field has changed massively between the first snapshot that I showed you at the last. Now, just condensing all of this into a graph, what we can plot on here now is just the vortex sheet strength at the separation point with distance moved and an x-axis. And this is what it looks like raw. And if we now, we see we have this very big variation in strength. But now instead, if we account for this changing in velocity, then we can see that, yes, it's not quite perfect, not quite straight, but it's much more constant. Despite the flow field changing so much. Now, to put this to a test, let's look at a different kinematic case. So in this case, we're moving our cylinder, but we're also spinning it very, very quickly. It's so that we shed one vortex from the bottom. And if we do this, and if we now extract the boundary layer vortex sheet, the strength at the separation point, we unfortunately see though that we have this constant decline. With time, the strength at the separation point is less and less and less. Again, we can't really use that to predict separation at all. But we can try and understand why this is happening with our toolkit of looking at how the individual boundary layer vortex sheets develop. So because we've already accounted for changing in velocity, this can now not be the case for this decline in vortex sheet strength. So the only other option that can be, the other culprit is really the vortex sheet due to free vorticity in the flow. And that changes a lot. So it wouldn't be, it seems to make sense that this is what's causing this change in strength. So just to highlight this, I suppose, is we're going to now plot the vortex sheet due to shed separation, strength on the y-axis, position on the x-axis, and with our circle showing us this point of separation. And now I'll just keep adding lines to this graph, and we just progress through time as we move from red to blue. And what you can see is that we have this consistent downward shift, basically, of our vortex sheet. So in this region that I've tried to shade in, and this region corresponds with basically the upstream half of our cylinder. So the opposite side of the cylinder where the vortex we've shed isn't really attaching to. So there seems to be a pattern here that with time, as we shed more and more vorticity, which moves away from the cylinder, we cause kind of a constant decrease of our vortex as a whole. So to understand this better, we propose to actually split up this vortex sheet to such separation into two more groups. And the first one is a vortex sheet due to the local vorticity. What do I mean with this? Well, if you have some vorticity that's very, very close to the cylinder, then to find its vortex sheet, you put a mirror image into the inside of our cylinder according to some relationship, which isn't really important. All that is important is that it's very close to the surface over here. Then to find the vortex sheet strength, what we do is we see the velocity that our real or red vortex induces everywhere along our surface, see what vorticity our imaginary vortex induces everywhere along the surface, and then we add these up, and that's our vortex sheet. Now, because here on the right, the velocity that we had of both vortices adds up, we have a high velocity, where on the opposite side of the cylinder, the velocities are basically will point in the opposite direction. So we have basically no contribution to the vortex sheet on the other side of the cylinder. And this is what I tried to show here, where we have a local vortex sheet strength, which is high, but everywhere else it's basically non-existent. And then we have a far field contribution, where if our vortex is, for example, infinitely far away, the extreme case, then we can plot one. The mirror image is now at the center of our cylinder. And now if we find the vortex sheet, we see by looking at the induced velocity, the red vortex, our real vortex, is so far away, it doesn't induce any velocity. Our mirror image induces a constant velocity everywhere, which means that in the case of the cylinder, we have a constant vortex sheet everywhere. So now in practice though, how do we define a real and a local and a far field vortex? You could either, I suppose, have a hard cutoff, but that's somewhat arbitrary. So what we've decided to do is use these two mechanisms of calculating the vortex sheet for each individual vortex. So what that means is that each vortex, basically, you could think of has a local contribution. So if a vortex is very close to the cylinder, then it has a high local contribution and only a very small far field contribution. Whereas if it's further away, then it has only a small local contribution, but a high far field contribution. And we now did this for all of the vorticity in our flow, and we can look at what patterns we spot. So on the left hand here is just our original vortex sheet due to separation, the one you saw before. And on the right, what you'll see in a moment is these two components. Your far field vortex sheet, which is just this straight line because we said it was uniform everywhere, and then your local vortex sheet. And as we step through time now, again, moving from the reds to the blues, we see that as our real vortex sheet moves down, or the reason why our total circulatory vortex moves down is that our far field contribution gains in strength. And that makes sense, I suppose, because with time, you have more and more vorticity advecting away into the far field. So it has, that vorticity begins to have a uniform contribution on the flow, whereas your local vortex sheet strength, due to all the vorticity constantly being shed and in close proximity to the cylinder, basically remains the same all the way along. Which means that, or one thing we can therefore do to see if we've understood this correctly, is apply it to the vortex sheet strength at separation point. So in red here, we had the raw value that you saw earlier. And now what we can do is we can account for this far field vorticity. We can just remove it basically and see what we get. And in this case, we get an almost constant strength vortex sheet at the separation point, even though the flow field changes a lot in time, showing us that we really have identified the core contributions to what causes the vortex sheet at the separation point to change correctly. One, in terms of the instantaneous flow velocity, and two, that it is this buildup of far field vorticity that causes this gradual decline in the vortex sheet strength at the separation point. And simply knowing this now can hopefully help better interpret any sort of data when we try to predict or measure the unsteady separation point, or even apply to the leading edge suction parameter for those of you who've heard of it. And one final thing we can do with this actually is that we can look at lots of different test cases and see how the strength at the separation point changes if it's just the raw data. So we're gonna collocate all of this on the left plot, where we have in this case, the strength at the separation point when we were just surging. So the first case you saw, we can add on top the case where we spin quickly, and we can add on top a case I haven't shown you, but where we spin slowly, where we separate from one side of the cylinder, and then we also separate from the other side of the cylinder. And if we now account for the rotation rate, and importantly, instantaneous velocity, as well as this far field contribution, then what we see is that they all actually line on top of each other. Not perfectly, to be fair, but given that there's quite a bit of uncertainty in the measurements and so forth, this is actually quite good, and really does show that we, I think, maybe have understood to some extent at least what the core contributions to the boundary layer vortex sheet are and why it behaves the way it does. So that's just a summary basically of this. Even though we saw the boundary layer, the point at which we have unsteady separation change a lot, we could see that if we account for an added mass vortex sheet, which forms due to surging or the surging velocity, and we account for the vortex sheet due to free vorticity, in particularly the local and importantly the far field vorticity, where it is really the far field vorticity that is playing an overarching role in causing the strength of the boundary layer vorticity to change at the separation point in time. And with this, to summarize kind of what we've been talking about, so we started off saying, look, unsteady flows are everywhere around us. We ideally want to model them very, very quickly using low order models. In low order models, we split up the forces often into individual contributions that we then solve using simple models and then superimpose them in order to make sure that we are not considering the same forces twice. We started off by looking at the fact that the boundary layer vortex sheet itself can be decomposed into individual contributions, where the rate of change of each can be linked to a force. We then saw that even though the vortex sheet looks the same and grows the same, whether it is our body or the flow accelerating, the origin is very, very different, which is important to consider so that we don't consider the same force twice. And then finally, we looked at the unsteady separation point, or the vortex sheet strength at the unsteady separation point, where we saw that changes quite a lot as our body moves. We then, however, saw that most of this motion or most of this variation is due to any changes in translation velocity, as well as due to far field vorticity building up as more of the shed vorticity moves away from the cylinder. And with that, yes, thank you very much for having me one more time. And if you have any questions, I'd be happy to answer that.
Yes, thank you, Pascal, for this very interesting presentation. I really enjoyed the physics and the very nice visualizations. So thanks. If there is any question, please, you can either unmute yourself and ask Pascal directly, or you can put that in the chat. So I have one question. So Pascal, do you need to make any assumption of the flow regime? And for does the flow has to be laminar, or it can be laminar turbulence, or even transitional flow? So
yes, so the one big assumption, as I said at the beginning, is I suppose you need to make sure your flow is two-dimensional. Because otherwise, I suppose everything does break down a bit, especially if you only do planar PIV like we do. Other than that, in terms of measuring boundary layer vortex sheet, in the method I described, where we divide the flow field up into little wedges and then integrate the velocity around that, I think that should, as long as you're taking an average flow field, I suppose, that should always work. In terms of how the results would look, so in terms of, once we count for free vorticity, that's like moved far away, and then we saw that the strength at the separation point kind of really remains constant. That we haven't looked into that much, so I'm not. I'm not sure whether that trend would then hold, or whether then just the way the flow separates is very different, so that you couldn't use that trend anymore.
I see. And I guess also this method, my second question actually is about geometry, but I guess you just, as long as it's two-dimensional, you can handle all kinds of geometry, like airfoil, all those things.
Yes, exactly. And one thing that does happen is that this to measure the boundary layer vortex sheet, if you have different shapes, it does sometimes become a bit more tricky. So we saw in one of the slides where we measured the boundary layer vortex sheet on our cylinder, that at the point where the flow separates, you get some iffy results, because you're drawing a line to differentiate between, you're saying, well, okay, down here, so if this down here is my surface, then you're saying, okay, here, this vorticity we're going to associate with the boundary layer, and then if we have a separating shear layer, you're saying, well, just above that, we're not going to consider that with the boundary layer anymore. So, the exact position of where we make that kind of decision of what vorticity we associate with where is a bit arbitrary, to be honest.
I see,
So for the cylinder, it actually works out really well because of just the geometry and how that shear layer separates. But we've worked on airfoils and applied the same mechanisms, and generally everything works there as well. But it's just that measuring the boundary layer vortex sheet at the separation point is a lot more tricky and a lot more noisy.
I see. I guess it's just very sensitive. It's more sensitive for the airfoils.
Exactly.
Very interesting.
Exactly. But in general, all these ideas work for any object.
Yep. Nice. Any question from the audience?
Yeah, I have like two questions, Pascal. So more like a clarification. So first of all, wonderful talk. So can you maybe share with us, or at least with me, your PhD thesis? So I assume it's like you mentioned it's like a PhD work. So I would like to dig in deep. So I have like two basically clarification would like to raise from you. One is you mentioned the unsteady separation point. What's the definition for the unsteady separation point? You mentioned that, but I don't think I have missed where you define that.
Yes. No, good point. In my case, I just used it as very simply of where does the boundary layer move away from the surface of our cylinder in our case. So where can you see that it's no longer following the surface, but it's moving off into the flow field, is what I used as the point of separation. So not using any sort of, looking at the shear stress or any sort of inflection points or anything like that.
So I think this maybe some of like, DNS, like,
Mm-hmm.
can be like a very interesting, like to reconfirm, like, what like
Mm-hmm. Mm-hmm.
experimentation, because as you mentioned, like, from the PIV, you're probably just eyeballing where the like separation
point. Yes, exactly. I mean, effectively what I took as the separation point is if you look at how the vortex sheet progresses, it's upstream of it, it's very smooth. And then as it gets to the separation point, you see the sudden drop off. Basically, I wrote my code so I find this drop off. And if you then plot that position on the vorticity data, like the vorticity contours, you see it matches up exactly as you would expect with where vorticity leaves the surface. But yeah, it's obviously not 100% accurate, I suppose, and mainly also, well, partly also because I suppose the limited resolution that you have in your PIV data to some extent. But yeah, so looking at it from a DNS perspective, definitely would be could be a little more precise.
More quantified, but anyways, like the result, like the as you mentioned, like to capture like a major contribution, and from like the result, it's very convincing to me. So that's one clarification. The second, like clarification that I would like to want from you is that basically from your first part of the talk, you mentioned that. Yes, I understand, like the vorticity, like the boundary vorticity, like come from different source, but like flow is similar, like for both X-ray to both X-rating cylinder in the still water, or the like the stationary structure in the X-rating flow. But like you also, like if I see it right, you also mentioned that atom mass force are similar to each other. Is that like a conclusion you just like get like from like the so basically like the atom mass coefficient or atom mass force for like one that accelerating in the still water and the one that like stationary in the accelerating flow is same? Is that like a conclusion you make?
So I suppose it's half true. So one, it again depends a bit how you specify everything, but I suppose in the accelerating case, you have you have a buoyancy force, which I just neglected due to the pressure gradient in the flow. And then I suppose you have an added mass or an inertial force, I suppose is what I'm trying to say. So if you consider both of these, then that's different to if you just have your body accelerating, where you just have the added mass force.
Okay. So I guess
maybe that's where the confusion came from.
Yeah, I think I'm missing that like part. You say like you lose like a buoyant force, because I was like, this seems to contradict to like what I learned like in the basic fluid mechanics for the waves, like the fluid corridor force, like it's always should be adding one like in the then like sorry.
No, but to be fair, I didn't mention that, so well spotted.
I think you mentioned, but I think like just like to focus on like the good material, like so like so again, like really wonderful, like if like you're willing to share your like a PhD thesis or like some paper to directly like I definitely want to like go into detail and like share with my students. So
yes, I can point you towards them at the end of it. But basically, if you just Google my name, then it should come up. It's all online, but I can pass on those things to you afterwards. And for anyone else that is interested. But otherwise, they will be online.
Thanks.
Yeah, nice discussion. And Xiaoyang asked this question. Many thanks for the fascinating presentation, Pascal. And do you or your team have planned to investigate the rotational cylinder, especially effects on lift?
So we looked into rotating cylinders. As part of my thesis, I suppose, just and looking at different spin rates. But mainly we use that to look at how the boundary. Well, by changing the spin rate, you change how the flow velocity looks like, so how the vorticity field looks like, just to create different test cases for these ideas that we presented. We didn't fully look into how how changing the rotational speed changes lift. I mean, we have the forces, and I have some plots of it that you see that if you, I mean, two things I suppose maybe takeaway points from that is that if you spin at a slow speed, and with that I mean a speed where the so imagine your cylinder is moving this way and you're spinning clockwise in my hand, then the top of the cylinder at some point, if you're spinning quickly enough, will spin quicker than you're moving, which means that and at that, once you go above this level, you only shed one vortex from the bottom of the cylinder. Whereas if you, so that would be then fast spinning, and that's the one case I showed, the first rotational case. If you spin, and in that case, I suppose your force just asymptotes to some steady state value with time. If you spin slower than that, you get alternate vortex shedding. And from there, you then, if you look at the force, you get this sinusoidal pattern. In the thesis, we look into it a bit, into how you can kind of explain this alternate vortex shedding pattern from a perspective of, again, vortex sheets. So just looking at it from a slightly different perspective. That's what we did. We also added an end plate at one point just to make sure how much it does affect things. And we saw that for the very high rotational speeds, as you would expect, it does make quite a big difference in terms of lift force. Though for like all the slower rotation cases, and if you're just surging, for our case, for our cylinder, which is 48 centimeters long and 6 centimeters wide, it didn't really make much of a difference. But yeah, for the future, I don't fully answer the question. I suppose I don't think we're going to be looking into spinning cylinders and lift in the future much, at the moment at least.
Okay. Any more questions from the audience? Yeah. So Rajiv has this question. So excellent talk, Pascal. Can you please briefly comment on the role of viscous effect in your circulation decomposition? I guess we briefly discussed that, yeah, but if you can elaborate on that.
So I suppose, your viscous effects, you have those in the real world because they create your boundary layer. The one viscous effect, which I didn't quite mention, which I don't know if this is towards this question or not, but is if you measure the real flow field using PIV, then you have your light sheet coming in from the side, and you have some reflection that you're always going to get, even if you color your cylinder matte black, which means that there's a very small, roughly 1 to 2 millimeters in our case, of a section of right next to the cylinder or a plate or any object where you can't capture any data because it's just obscured. So what we can, however, do is we can recover the total amount of vorticity in this situation. Because if we've tracked how quickly we're spinning the cylinder and how quickly we're moving it, we at each point in time know exactly what velocity of the cylinder surface is. So then what we can do is we can interpolate between the cylinder surface velocity, which we know, to our first vector in the PIV data to get the total amount of vorticity. Of course, though, we don't know the wall normal distribution of that vorticity. So you don't know whether that vorticity is mainly in like 2 millimeters away from your cylinder, or if most of it is actually within like right next to the wall. So that, I suppose, those viscous effects we can't determine. Other than that, in terms of my decomposition, really it shouldn't affect it that much because you have your vortex sheet due to rotation. That is simply an inviscid calculation that you're doing. You've got it due to translation, that's also inviscid. Then the one part with the viscosity, I suppose, comes in the real flows if you've shed vorticity and how that induces and then that related vortex sheet. But yeah, other than that, I don't think it makes that much of a difference. But maybe I've also misunderstood the question slightly.
Pascal,
please let me know.
Hi, Pascal. Let me rephrase.
Okay.
So this is a highly nonlinear couple. You got the unsteady, you got the circulatory force, and your viscous forces is highly nonlinearly coupled, and you are assuming there's some assumption, which is fine, is your viscous effects, you can completely meaning your unsteady forces you can decompose and in linear way, right? And that nonlinear effects are not being accounted here. So there's a range here, and also possibly is applicable, this whole assumption, right? So it's a range dependent. What range of Reynolds number is that decomposition, because it's highly nonlinear, unsteady, inviscid, added mass, circulation, and viscosity, they are interacting all together, right? So my point was, is there any range you can point out this whole decomposition is applicable?
Right, okay. Sorry, I completely misunderstood the question then. So, I mean, we tested in a range between 5,000 to 25,000, I think, in terms of Reynolds numbers. And there, when we do our force decomposition, we get just purely looking at the, vorticity field and comparing that to the force balance measurements we get a very good match. But we never strayed outside that scope. So I fear I can't put any numbers on when then that would break down, when the non-linear effects would become important. But at least within our regime, at least, as long as you're looking for an overall trend in forces and you don't want to be within a % of the real force, then you could, then it still worked out for us at least.
Okay, sounds good. Yeah, this is what I was expecting.
Okay.
Yeah, there's a certain range, and this whole decomposition is working nicely. Yeah. Because there was a big debate from Sarkaya's paper, probably you have seen those. So a lot of controversy how much we can decompose. This is a big deal here if you can decompose all these forces. But it's always range dependent.
Yes, that is true.
All right, thank you.
Thank you.
Hey, all nice, very discussion. So I guess if there's no more question, that's all for today. Let's thank Pascal again for his very nice presentation, and if with his permission, and we can share his thesis with all the our mailing drives, mailing subscriptions. So with that, thank you for attending this seminar, and we will see you next week. All right, see you.
All right, thank you.
Bye-bye.
Yeah, bye.
That's wonderful.